Welcome to this episode on elastic collisions, part of our momentum series. Today, we'll explore a special type of collision where objects bounce perfectly, conserving their kinetic energy. This is a fascinating topic that reveals the fundamental principles of energy and momentum conservation in physics. An elastic collision is a collision where objects bounce off each other without losing kinetic energy. When two objects collide elastically, they separate after impact with the same total kinetic energy they had before the collision. The key characteristic is that the total kinetic energy of the system remains constant before and after impact. No energy is lost to heat, sound, or deformation. In elastic collisions, two conservation laws are at play. First, momentum is always conserved in all types of collisions, whether elastic or inelastic. Second, kinetic energy is conserved only in elastic collisions. This makes elastic collisions unique because both quantities remain constant throughout the collision process. The conservation of momentum states that m1v1i plus m2v2i equals m1v1f plus m2v2f in words. This means the total momentum before collision equals the total momentum after collision. The subscript I represents initial values, and the subscript f represents final values after the collision. The conservation of kinetic energy is expressed as 1/2 m1v1i squared plus 1/2 m2v2i squared equals 1/2 m1v1f squared plus 1/2 m2v2f squared. This equation tells us that the total kinetic energy before collision equals the total kinetic energy after collision. This is what makes a collision elastic. There's an elegant principle for elastic collisions, the relative velocity relationship. It states that v1i minus v2i equals negative of v1f minus v2f. In simple terms, the speed of approach equals the speed of separation. Objects approach each other at the same relative speed as they separate after the collision, just in opposite directions. By combining the conservation laws, we can derive formulas for the final velocities. For object 1, v1f equals the quantity m1 minus m2 times v1i plus 2m2 times v2i, all divided by m1 plus m2. For object 2, v2f equals the quantity m2 minus m1 times v2 I plus 2m1 times v1i, all divided by m1 plus m2. These formulas allow us to calculate the velocities after collision given the initial conditions. Let's work through an example. A 2-kilogram ball moving at 5 meters per second collides head-on with a 3-kilogram ball moving at 2 meters per second in the opposite direction. Find their velocities after the elastic collision. We're given m1 equals 2 kilograms, v1i equals positive 5 meters per second, m2 equals 3 kilograms, and v2i equals negative 2 meters per second. The negative sign indicates opposite direction. Using our formulas, for object 1 final velocity, v1f equals the quantity 2 minus 3 times 5 plus 2 times 3 times negative 2, all divided by 2 plus 3. This gives us negative 5 minus 12 divided by 5, which equals negative 3.4 meters per second. For object 2 final velocity, v2f equals the quantity 3 minus 2 times negative 2 plus 2 times 5, all divided by 2 plus 3. This gives us negative 2 plus 20 divided by 5, which equals positive 3.6 meters per second. Notice how the first ball reversed direction after the collision. Where do we see elastic collisions in real life? Billiard balls provide nearly perfect elastic collisions on the table. At the atomic level, gas molecules colliding exhibit elastic behavior. Super balls made of high-bounce rubber approximate elastic collisions. Newton's cradle demonstrates both momentum and energy conservation beautifully. However, it's important to note that perfectly elastic collisions are rare in everyday life. Most real collisions lose some energy to heat, sound, or deformation. Let's review the key takeaways. In elastic collisions, both momentum and kinetic energy are conserved. The speed of approach equals the speed of separation, which is a unique property of elastic collisions. The final velocities depend on the masses and initial velocities of the colliding objects. While ideal elastic collisions are rare in nature, they serve as useful models for understanding energy conservation. Master these concepts, and you'll have a solid foundation for understanding collision physics. Thank you for watching.
If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.